All right, good afternoon, everyone. Thanks for the introduction. Yeah, I'll be presenting my work on designing a small intermediate representation for high-level synthesis with functional parallel patterns. All right, so since I'll be describing a new language, I guess I'd better start by clarifying what sorts of programs am I looking to express with this language. Specifically, I'm looking to describe streaming accelerators that run on an FPGA. Now, FPGAs are interesting because they're a nice middle ground between application-specific integrated circuits and general-purpose processors like CPUs and GPUs. On one hand, you have the flexibility to really customize your hardware for your specific app, which helps with power efficiency and performance and so on. But on the other hand, you don't incur the cost of manufacturing your own custom chip. You just reprogram the device. Now, let's say that somewhere on this FPGA, you have a component that performs a dot product. And for illustration, I'll just use these simple inputs 1, 2, 3, 4, and 5, 6, 7, 8. Now, in a streaming accelerator, these inputs are provided piece by piece rather than all at once. So for example, maybe at the first clock cycle, we provide the inputs 1 and 5. And then at the next clock cycle, 2 and 6, and then 3, 7, and then 4, 8. And then later, we should get the answer, which is 70 in this case. So what options do we have for designing these sorts of streaming accelerators? Well, traditionally, you would use a hardware description language like VHDL or Verilog, which gives you a lot of control over the result, but it's very low level and verbose, right? It's kind of like writing your software in assembly. Like maybe sometimes we need that control, but hopefully there's a higher level option, right? And indeed, there's been a lot of work on high-level synthesis, especially on converting languages like C++ to VHDL and Verilog. This is, and this sort of imperative programming model that you have in C++ with mutable variables, loops, dynamic memory allocation, that makes a lot of sense on a CPU, but not as much sense if you're trying to design a circuit, right? So what I'd like to focus on for this talk is another approach in which we use parallel patterns from the functional programming paradigm, like map and reduce and zip and so on, in order to build up these streaming accelerators. All right, so let me explain this functional style dot product program in detail, since I'll be referring to it throughout the presentation. We have two inputs here, U and V, and these are both streams of 16-bit unsigned integers, which means that for each of these inputs, we'll be receiving one 16-bit unsigned integer per clock cycle, right? And they both have a length of 4, so I can reuse the same example inputs 1, 2, 3, 4, and 5, 6, 7, 8. So probably the first thing we want to do is we want to combine these two streams of numbers into a single stream with pairs of numbers, which we can do with this parallel pattern zip. So in this example, 1 will be paired up with 5, and 2 with 6, and so on. Next, we want to multiply each of these pairs of numbers, which we can do with this parallel pattern stream map. Stream map just applies a function, in this case multiplication, to every element of the input stream. So we should get as output from map 1 times 5, 2 times 6, 3 times 7, and 4 times 8. And then finally, we want to add up all these numbers, which we can do with the parallel pattern stream reduce. Reduce just combines a whole sequence of numbers into a single number with some sort of aggregation function, in this case, addition. So as before, the result should be 70. And there's a very natural correspondence between this sequence of parallel patterns and a 3-stage pipeline, where the first pipeline just sort of zips the two streams, the next stage does the multiplication, and the last stage performs this accumulation with an adder, right? But now you might be wondering, hey, Louis, why should we have, whoop, I jumped the gun. Or no, it's fine. Okay, no, it's fine, sorry. Yeah, so you might be wondering, hey, why do we have this register in the first pipeline? It's not in the first stage. It's not actually doing any work, right? And indeed, in prior works, like Sure, for example, you can optimize these programs built out of these parallel patterns using simple rewrite rules. So for example, let's say our language has another parallel pattern called stream map 2 that's basically equivalent to zip followed by map, but it does it in a single step. Well, then in our compiler, whenever we see zip followed by map, we can rewrite it, or in other words, just replace it with a call to stream map 2. And that will have the effect of combining our first two pipeline stages, which eliminates the register, right? Cool. So with this functional parallel pattern approach, there's a nice correspondence between the source code and the hardware, and the compiler can kind of optimize the programs using these simple rewrite rules. So then what's the drawback, other than, I guess, people being unfamiliar maybe with these parallel patterns? Well, one drawback is that if you want your language to be useful, you need a lot of these parallel patterns, right? This is kind of a hassle. It's particularly a hassle to add new parallel patterns to your language because you need to, implement this operator in VHDL or Verilog or whatever your target language is, which is kind of a pain. You also need to explain how does this new parallel pattern interact with all the previous ones, right? How do I fuse this new one with map? How do I fuse it with zip? How do I fuse it with reduce? And so on. And also, if you think back to the previous example where we, fuse zip with map to map2, if you don't have map2 in your language, you're out of luck. You just can't implement that rewrite rule, right? So what I'm going to show in this presentation is that you can express all the operators that I listed on the previous slide with just 3 stream-related primitives, and also that this is a useful thing to do. Besides simplifying hardware generation and optimization, you actually get more resource-efficient results at the end of the day. All right, how are we going to do this? Well, we can take inspiration from prior works on array programming, which expressed array computations with just a very small IR. Specifically, there's one constructor for arrays. You can build an array of length n, where the element at index I is given by some arbitrary function f. And there's also one extractor for arrays. You can ask for the element at index I in some existing array, right? And using these 2 building blocks, you can express all kinds of higher-level operations on arrays. So for example, the ith element in the output of map is just f applied to the ith element in the input array v. And likewise, the ith element in the output of zip is just the ith element of v1 paired with the ith element of v2, right? So now I'd like to use the same idea, but for describing streaming accelerators, right? So in prior works, you've got this input language with, stream zip, stream map, stream reduce. The compiler applies rewrite rules to try to optimize this. And then prior works basically just translate this directly to a hardware description language. What I'm suggesting is that instead, we should add a new intermediate representation, a small intermediate representation, which I'm calling Sirop, to this compilation pipeline. So we first lower the higher level language down to this intermediate representation, and then we apply optimization and hardware generation on the smaller IR, which is easier. And in this IR, there is, like with the array programming works, there's one constructor for streams called sbuild. There's one extractor for streams called sdata, which just gives you the next element in the stream. And there's also a mechanism for sharing a stream between multiple consumers. All right, now one more thing before I get into some examples of using this IR, I'd better clarify what kind of hardware we're trying to generate. So specifically, we're looking to generate a pipeline in which stages communicate with this handshake protocol. So every stage sends n bits of data to its consumer, along with the signal saying whether the data is currently valid. Conversely, the consumer sends back a signal saying whether it's ready to receive that data. If the consumer is not ready to receive the data yet, the producer had better not move on to the next element in the stream yet. And within each of these stages, you might want to have some internal state, like the accumulator inside of stream reduce, right? The running total. All right, let me get into some examples. So probably one of the simplest programs you can write in this IR is just building a stream of length 4 in which the output is always 42 and it's always valid, right? This expression evaluates to the stream 42, 42, 42, 42. And the hardware for it is very straightforward. You're just constantly sending the value 42 into the pipeline register. Yeah, what if you want to have some internal state in your stage? Well, we can build a stream of length 4 where the output is, instead of 42, it's I. And here I is an accumulator. It's a 2-bit unsigned integer, where the initial value is 0, and the value at the next time step will be the current value of I plus 1, right? In this case, this expression will evaluate to 0, which is the initial value, 1, which is the next value, and then 2, and then 3, right? And in hardware, you'll have still the pipeline register at the output of the stage. You'll have register for the accumulator I, and you'll have an adder that increments the accumulator all the time, right? Hopefully it's OK so far. Now, let's say you want to have a stage with some inputs that reads data from another stage, right? So like stream map. Well, in that case, you can declare a producer called P. Continuing from the dot product example, we'll say that P is a stream of pairs of 16-bit unsigned integers. The stream itself can be like any stream expression. It can be an S-build expression. It can be a variable, whatever. And in this case, for stream map, we're always ready to receive the next element. The output of stream map then, again, in the dot product example where we're doing multiplication, you'll compute that by reading the data from the producer and then multiplying element 0 by element 1, right? And the output is always valid. And in hardware, what's going to happen is that the data from the producer stream is just going to be fed right into the multiplier, and the output of the multiplier will be sent to the pipeline register, right? Stream zip is very similar. In this case, you'll have 2 producers. Again, we're always ready for both of them. And the output of zip is just the data from the first producer paired with the data from the second producer, right? Now, you might be wondering, hey, Louis, why is the output always valid? And why are we always ready? Like, if one of the producers has validated but the other one doesn't, don't we have to wait? Great question. So if you're using VHDL, then indeed, you would have to take care to carefully follow the handshake protocol so as to not drop elements from one of the producers. But in the IR, you can actually kind of pretend that as soon as the ready expression evaluates to true, the data will arrive immediately. And then the C-level compiler will take care to insert some extra logic in the hardware to make sure that a logical time step doesn't happen until the data is actually valid, right? Which is, I think, quite a useful abstraction. All right, one more example to put everything together. Stream reduce. So as before, we have one producer P, always ready for it. We have an accumulator for the sum. It starts at 0, and the value at the next time step is the current value of the sum plus the data from the stream, right? That's also the output of reduce. But when does reduce have valid output? Only once we've finished reading the stream, right? So we can add another accumulator I, which starts at 0, and it counts up at every step. And the output of stream reduce is only valid once I is about to hit 4, which is the length of our stream, right? In hardware, again, there will be the pipeline register. There's going to be a register for the sum. And there's going to be an adder to update the sum. And here I'm just omitting the register for I along with all the extra handshake logic that gets added for the valid and ready signals that I mentioned on the previous slide. Just for completeness, here's the full dot product example. So we've already seen 2 slides ago how to implement zip. There it is again. This is used as the input for map, which we saw 3 slides ago. And this is used as the input for reduce, which we saw on the previous slide. So nothing new here, just kind of putting everything together. All right, so we've seen how to implement these higher level, parallel patterns like zip and map and reduce in this IR, and hopefully you have some intuition about how it translates to hardware. But now, what about optimization? Can we still do things like fusion, for example? And the answer is yes. Otherwise, I probably wouldn't have brought it up. So if I've explained myself clearly so far, hopefully you can imagine how instead of having these 2 producers pairing up their data and then multiplying them later, we can just multiply the data immediately, right? And that looks like this, right? So 2 producers, multiply the data, there you go. And exactly as before, this will combine our first 2 stages into a single stage and get rid of the first register, which maybe we don't want. All right. Now, is the hardware generated by Sirop actually any good? Well, to evaluate this, I compared the Sirop compiler with 3 prior works. There's the Intel HLS compiler, which lets you write code in C++. And then there are 2 research compilers for this functional HLS. There's Sure and there's Etherling. On the x-axis, you can see various benchmarks ranging from small examples like a dot product up to larger examples like matrix-matrix multiplication, Sobel filter, image sharpening, stuff like that. And on the y-axis, you can see there are 2 measures of hardware quality. There's the number of adaptive logic modules that tells you, how much area is your circuit taking up, how many FPGA resources does it consume. And there's the latency, the number of clock cycles from the first input till the very last output. If we look at the latency first, you can see it's pretty much the same for every tool. So in other words, Sirop is not degrading the performance in any way. And if we look at the number of ALMs, here it is for Intel HLS. Here it is for the functional HLS tools. So you can see, sometimes they're doing better than Intel HLS. Sometimes they're doing a little bit worse. And here it is for Sirop. You can see that, in general, it's doing better than any of the prior tools. And in fact, it's really not obvious because it's on a log scale. But on average, it's actually using much fewer ALMs than the prior works, like 76% fewer than Intel HLS, 60% fewer for the other tools, which I think is kind of cool. All right, so long story short, by adding this extra IR Sirop into our compilation pipeline, you can still express all the same high-level programs as you could before. It becomes easier to do hardware generation and optimization, right? Because you have a smaller language to deal with. And you actually get better, or specifically more resource-efficient results at the end of the day. If you're interested in hearing more, I encourage you to take a look at the paper. You can try the compiler for yourself. It's all open source. Or you can ask questions right now.
Yeah, the program chair taking priority, that's not good. Yeah, thanks, very nice talk. I was wondering, how does it compare to Stream HLS, like that work from Shiru Zhang and Jason Kong? So they've been also working sort of DSLs for streaming applications down to HLS tools.
Yeah. Oh man, I read about this a while ago, but I forget what their approach was exactly, so I'm not sure, sorry.
Yeah, so I'm wondering maybe, so their approach is similar to what like companies are doing, maybe building infrastructure with MLIR, right? Where the dot product is sort of a name operation that you know what it does.
Yeah.
And so they build optimizations from those MLIR named operations.
Yeah.
So it's a different approach, because then you have, so the IR is, say, richer because it does not encode a schedule. Like I think your IR scales encode a little bit of a way of putting things together, right?
Yeah, basically. So I guess in my approach, you can kind of simulate the IR to get, basically a cycle accurate idea of what's going on.
Whereas here is more, say, maybe declarative in a sense, right? Because you have some name operations, you have a convolution 2D with some stride, and out of there you can generate streaming-based accelerators. So I was wondering how that compares, but yeah, maybe we can take that offline.
Yeah, sure. I mean, I guess with this approach, like again, we're still starting with these sort of high-level operations, so you can, add all these, high-level things like zip and map, and you could totally add something like stream conv 2D, which the programmer doesn't have to worry about how it works, and then the compiler writer takes care of implementing that. Which I guess eventually has to happen with Stream HLS as well, right?
Yeah, exactly.
Yeah,
hey, thanks for the great talk, Louis. This is Rachit from MIT. I had a question about your results. Did you measure the number of registers that you use up in your design, or is ALM, I imagine, is a measure of logic like LUTs equivalent, essentially?
Yeah, great question. So I'm doing all this on Quartus, and my understanding is that in Quartus, an ALM includes registers and logic.
And it doesn't break down for you the logic versus register?
I think it does show the number of registers, but I didn't record that, sorry.
I see. Because traditionally, tools like Etherling generate a lot more registers. So that's the actual trade-off they end up having. They have more registers and therefore less logic oftentimes. For your Fmax, did you pin it to 175 for all the designs, or did you do a search for the Fmax on all of the designs based on the slack you had left?
So I just used 175 in general because that's what Etherling used for their evaluation. In general, a lot of, so I didn't really search very carefully, but from what I've seen, like Quartus's estimates, a lot of the designs hit, at least the, 200 plus. Yeah. So it's, yeah, the Fmax could definitely be better, by inserting more stages and so on. But I didn't do a lot of work on that.
Understood. And the latency is wall clock time with respect to 175 megahertz and the number of cycles.
Yeah, sorry, the latency is in clock cycles.
I see. Okay. Thank you.
Yeah, sorry, maybe it wasn't clear.
Any other questions? Maybe I can have one more question,
Yeah.
very last question. I was very surprised because you said every operator could be represented with this Sirop. So what was the most challenging operator you like to build with your Sirop?
I guess one that's maybe a little bit tricky is, I don't know if I have it here. Yeah, repeat. If you want to repeat a stream, you kind of want to kind of read the whole stream into memory, then read it back out from memory. Which, yeah, I had to do a little bit of work there to get Quartus to kind of recognize the VHDL code that I generated as something that can be a memory block. But yeah, hopefully it's kind of intuitive why you can express all these operators in Sirop. Like you kind of have all the ingredients that you need, right? You can read from some other stream. You have some, registers basically that can all be updated in basically arbitrary ways. In fact, fun fact, this IR is Turing complete. It's kind of cool.
Yeah, thank you.
Yeah, hopefully that answers your question.
Yeah, sure. Any more questions? Let's thank to our speaker once again, please.